Hello, this is Paul Green with O'Brien and Gear. The presentation is about liquid fraction of digestate treatment. The issue is that anaerobic digesters bring in large quantities of organics and nutrients in their feed stream. Digesters that separate solids can be left with liquid material that is high in organics, known as BOD, and nutrients. Typical analysis of this liquid fraction is very high in BOD, ammonia, phosphorus, and temperature. Priorities would be, the most preferred would be to recover, concentrate, sell, and monetize the nutrients. A less desired scenario would be to destroy the nutrients, or to remove them, eliminate them, or to discharge them. Also, weather issues can come into play where disposing of liquid fraction in cold climates, when the ground is frozen, can be challenging. What are some of the solutions to dealing with the liquid fraction? There's membrane choices, including microfiltration and ultrafiltration that remove macromolecules. Reverse osmosis, or RO, is a total filtration of all the compounds in the water. Ammonia removal can be done separately by stripping and recovery, concentration through RO, Anammox biological treatment. Phosphorus removal, or struvite recovery, is achievable. Biological treatment can be done through sequencing batch reactors, moving bed bioreactors, membrane bioreactors, or high-rate anaerobic systems. Typical discharge point for liquid fraction is a local sewer, a local stream, or on farm fields. So let's start with nitrogen removal. One way to get rid of nitrogen is through biological treatment. Nitrification is the biological conversion of ammonia to nitrate. On occasion, nitrate can be discharged to the environment. In those cases where total nitrogen removal is required, denitrification is done, where the system biologically converts nitrate to nitrogen gas. And the new technology out there is a shortcut shunt process, otherwise known as Anammox, that directly converts ammonia to nitrogen gas. Some economic considerations of these biological systems include their footprint, their capital costs, their operating costs, and the temperature they need to be running at. As far as membrane filtration goes, first is microfiltration, ultrafiltration, to filter out macromolecules and suspended solids that come out of the dewatering device of the digester. These can be used as pre-treatment ahead of reverse osmosis. They generally run at about 50 to 100 psi, and they have about a 2 to 5% back pulse stream of the feed stream. They don't filter out things like ammonia, phosphorus, or other nutrients, and you can get BOD removal through these technologies. RO is the next most advanced membrane filtration system, and it runs at about 200 to 1,000 pounds of driving pressure and can impart a significant parasitic load on the plant. It generates about a 20% concentrated stream of concentrated nutrients that one would hopefully be able to monetize. The membranes need to be cleaned fairly frequently, use microfiltration as pre-treatment, and there's several configurations of RO systems. There's a spiral wound membrane sheet, and there's also a flat sheet system that uses a vibratory shearing action to keep the flux rates up across the membrane and keep it from plugging. Various biological systems are available. There are anaerobic systems and there are aerobic systems. Anaerobic systems can be used following an anaerobic digester because they're able to convert soluble organics in a very high rate fashion. So it's getting additional biomethane at the site compared to what just comes from the upfront digester. Aerobic systems run in the presence of oxygen. They use electricity through a blower system to provide the oxygen, and they're better for lower strength waters. Anammox is targeted squarely at high nitrogen streams for removing ammonia. Loading rates can vary depending on the technology. Some systems are fairly compact. Other systems take up a fair amount of land area, depending on what kind of loading rate you can apply to these systems. First, let's talk about what a moving bed bioreactor is. It's an aerobic system that uses plastic media to provide an environment for the bacteria to live on. As shown in the picture here, there's thousands and thousands of pieces of this plastic media that move in a suspended fashion in the aerated tank. They have a very high surface area, and they're good for pre-treating the liquid fraction of digestate to sewer, in that you're getting 70 to 90% removal, has a small footprint, low operator attention, they're available in pre-engineered systems, and they handle wide swings in load. Here's a case study of a moving bed bioreactor system for a system in the Midwest US. In this case, it had a high strength wastewater, and they had to reduce their BOD level to discharge the municipal treatment plant. Their BOD was very elevated, and in a single stage MBBR treatment, they were able to get to less than 400 milligrams per liter of BOD through a system that implemented a moving bed bioreactor. This is the process flow diagram of the case study that includes all the various unit operations. This is a layout of the system, and the final system had about a 34-foot diameter facility that came as a field-erected tank using MBBR technology, as well as some pumps and blowers and nutrient feed skids that were inside an equipment building. MBBR units are available from some vendors based on various standard configurations of mass loading. So in these scenarios, small systems can range from 500 pounds of BOD per day in factory-built units, all the way up to field-erected units that range from 5,000 pounds of BOD up to 20,000 pounds of BOD per day in pre-engineered systems. Here's a picture of a packaged MBBR system that includes equalization, the reactor basin, and a storage system, as well as showing some process equipment inside of a building. Field-erected MBBR units can be roughly 25 feet tall and be of a variety of diameters based on the particular project. The next type of biological system is known as a suspended growth system, also called activated sludge. Suspended growth systems, they have aeration followed by liquid-solid separation and return the biomass to the aeration tank. They can run as continuous flow-through systems or as a batch operation as an SBR, sequencing batch reactor. They're good for when BOD is lower than 8 or 10,000 ppm, and they can provide excellent removal efficiency. They are low cost, widely applied, and can be very effective for high removal efficiencies on liquid digestates. Membrane bioreactors are a form of suspended growth technology similar to the past slide. However, there's a membrane barrier on the back end of the system that provides an additional level of treatment. So the fact that the membrane barrier is there, removal efficiencies are significantly higher, provides water that could be reused at the digester facility for recycle, for diluting incoming wastes, or it can be discharged to a local surface water or easily discharged to a local treatment plant. Anaerobic systems that are known as high-rate anaerobic typically will run as an upflow reactor, and they use a granular sludge system. They do well with carbohydrates, and they can convert those to methane in a very fast loading rate and provide good BOD removal efficiency. Their advantages include small footprint, they do not use much power, and they provide additional biogas, biomethane for the facility. So to compare these various biological treatment systems for BOD and ammonia removal, you can compare them based on their removal efficiency from medium to high. Their power usage also ranges from medium to high. Their footprint varies significantly. They're different in that do they generate biogas or not. And they also can generate additional solids that need to be managed from the site. Sometimes they need to be managed as a waste. Sometimes these solids could be recycled to the head of the digester and further processed. On the note of sludge generation, sludge can be predicted how much will come from these processes, and anaerobic systems generate much less sludge than the aerobic systems, which tend to have a much higher waste sludge generation rate. Another technique for managing ammonia from the site is ammonia stripping. It forces ammonia out of solution using forced air or a vacuum, favors a high pH of greater than 9, thus requires caustic injection and heat to get it over 110 Fahrenheit. The ammonia will generally be captured in the off gas by reacting with acid and forming a compound like ammonium sulfate. So this is done in the first pack column where air is introduced into the bottom of the column, your high nitrogen liquid is introduced to the top, your deammonified digestate comes out the bottom. So scrub vapors come out of the top that would include the ammonia-laden vapor. So that enters the second column where the ammonia needs to be removed from the vapor. So sulfuric acid is reacted in a countercurrent fashion with the vapor, and ammonium sulfate solution comes out the end of the process. So phosphorus can be recovered through a technology known as struvite removal. This process generates high quality phosphorus fertilizer pellets, and it's known as a struvite cone at times. These struvite cones introduce material near the bottom. Sometimes chemicals will need to be added, and struvite comes out the bottom after the particles have had a chance to react in a circular fashion inside the cone. These are typical struvite cones, and here's a shot of what the powdered struvite looks like coming out of the process. The struvite system can achieve very high phosphorus capture rates, and the material is easily bagged and shipped off-site and sold as a value-added product. Another technology for nitrogen removal is called anammox, sometimes called shortcut denitrification. It's a biological process that converts ammonia to nitrogen gas in a single process step. You can get about 90% removal efficiency. So if the projects require more than 90%, downstream polishing may be required. One of its key features is it provides savings on power, chemicals, and footprint over other approaches. So I thank you for your kind attention. My name is Paul Green. Here's my contact information, and we'd encourage you to reach out to O'Brien Gear for any type of support needed on anaerobic digester liquid fraction projects or anything pertaining to digester design, construction, or project delivery. Thank you.